So we're looking at a lesson on quadrilaterals, and here you can see that there's a nice little flow chart that talks about the relationships between different quadrilaterals. And yeah, I mean, I made it myself, which means that it's probably inherently flawed, but I think it does a decent job of getting the idea across. And then a corresponding table below that kind of gets at the important relationships between or among the different types of quadrilaterals. And this answer key will be posted on my website, so you don't have to worry about pausing the video necessarily to take note of every single thing. But I'm just going to glance over to page 2, where I've completed these problems. I'm not going to go over them because I think that they're pretty straightforward in terms of the explanations that I provided. If you have any questions, it's probably going to be related to numbers 1 through 8 at the top. So message me with those questions, because really I think it's more on an individual level, because if I were to go through them and say, well, number 1, a rectangle is a parallelogram always. Why? Because that's always true. You know, if you have additional questions, I at least can try to tailor it to the individual student. Page 3, same general idea. The twist on this page was, I think, number 8, part E. Aside from the fact that on my answer key I forgot to put little M's and notation in front of C and E, part E had that little extra component of having to do the Pythagorean theorem with the solution being a radical. Now, depending on the directions on an assessment, it might call for an answer to be in radical form. It might call for an answer to be in decimal form, which is why we reviewed those in the last lesson. All right, the concept of simplifying radicals. All right. But our focus in this video is going to be on the proof part of things, all right? Because we will have to perform these proofs, huh? And so I figured I'd take you through the most popular of the proofs. So rectangle ABDC. All right, that's not a typo in the formation of the letters in the given sentence. Honestly, it was a typo in how I created the rectangle to begin with. I meant to do it consecutively ABCD, but I labeled it ABDC, so the notation had to correspond with that. Another thing that probably should be mentioned here, although it's pretty obvious, with diagonal BC. All right, I'll take that as a typo. And I always do that. I don't know why. Given. All right, so our job here is to prove BAC and CDB, sorry, force of habit, are congruent to one another. All right? So basically, this question is asking us to take everything that we know about a rectangle and use it to help us to prove that two triangles are congruent. All right. So what I'm going to say here is that angle A could be no other thing, so we'll just call it angle A, is congruent to angle D in a rectangle. Rectangle. All angles are right angles, semicolon. All right angles are congruent. All right, so I'm going to jot that down. Surprisingly, we are we're 2 steps away. It's just a question of what 2 steps you want to use. All right, I'm going to use the fact that opposite sides in a rectangle are congruent. So I'm going to say AC is congruent to BD, and AB is congruent to CD in a rectangle opposite sides are congruent. So get a little meh here and another meh and meh, right? Meh and meh, right? So that'll pretty much do it, because now we have side angle side. The side angle side axiom showing us that triangle BAC is congruent to triangle CDB. And that's the SAS axiom. SAS axiom. All right. Not the similarity axiom, but the congruence axiom. By not putting the similarity symbol in there, we know it's the congruence axiom. We could have gone with hypotenuse leg theorem, but then just play that out. You would have had to state that these are two right triangles, so that would have given us an extra line in our statement reasons. And it, it might be okay, might not. Depends on what you want to do. All right. Now, so in this case, we were proving two triangles are congruent, and we were given the fact that it's a rectangle. Here, we need to prove that a figure is a parallelogram and that it's starting off as a quadrilateral. So I didn't include a diagram here because it's supposed to end up being a parallelogram, but what if it's not? I mean, it's gonna be, because that's what we're proving, but what if it's not? So the way things work in the quote-unquote real world is that we try to prove things, but it doesn't always end up being something that you can prove. So in theory, what I should do is just draw some arbitrary quadrilateral that's not necessarily a parallelogram. But in this case, because I know it's going to work out, and those are the only kind of problems that I would give you, I'm going to draw a parallelogram. All right? Assuming my pen wants to work. Yeah, for some reason. Oh, because I have this thing. Foolish. All right, so quadrilateral A, B, C, D. So it doesn't matter where you start with your A, just be consecutive about it. So A, B, C, D, counterclockwise, clockwise, it doesn't matter. Diagonal AC. Oh boy, you see that's my big issue here, the drawing part, and constantly making small mistakes that I have to correct. All right, I'm going to leave it like that and go with it. DC is congruent to AB. Angle ADC, so this one right now, that I still have my line draw tool on, so one of those aforementioned small mistakes that I always have to correct. ADC congruent to ABC, and DAC is congruent to CBA, collective bargaining agreement. BCA, sorry, the bargaining collective agreement. All right. So, got some possibilities. Lots of possibilities. First thing I got to do is get all this given stuff in here. So, 1, and I'll bring my annotation tool box up here. Quad for quadrilateral. It's not going to mean quadratic in this context. With diag. What else could that stand for in a geometry class? DC congruent to AB angle ADC congruent to angle ABC angle DAC congruent to angle BCA. I remember when I was learning about proofs when I was a student, like 5 years ago. I remember students complaining, man, we have to write all this given stuff down. So you're telling me that if I don't write this given stuff down, I'm going to lose credit? And I remember thinking to myself, wait a minute, you're going to give us credit just for writing that down? That's great. At least I know I'm going to get something. So I don't have to do anything else right, and I'm still going to get credit on this problem. All right, sign me up. All right, that's a little something. All right, so everything here has been established for us. We can actually jump, and I'm going to do this right away just because, you know, maybe it's relevant, maybe it's not, but it's something we can do. Triangle ADC is congruent to triangle, come on, pen, don't fail me now, ABC. And I charged it right before this session. And that would be by the angle side axiom. All right, so we got a little something cooking here. So there's a bunch of ways to prove a parallelogram is a parallelogram. A quadrilateral is a parallelogram. We could prove that the opposite sides are parallel. We could prove that, well, if we prove it's a rectangle, then it's a parallelogram, but there's really not enough there to show that this is a rectangle because, you know, if something is a rectangle, then it has to be already be a parallelogram. If the diagonals bisect each other, then it's going to be a parallelogram, right? So those are some things that could play out. But another one, the one that if it works, if it's present, it's really nice because it streamlines everything nicely, is the fact that if a quadrilateral is made up of two congruent triangles, it is a parallelogram. So that's what we're going with. And we're going to use this symbol here to represent a parallelogram, ABCD. Now, we're never going to get that confused with a rhombus because we're not going to use a symbol to represent a rhombus. All right? So, parallelogram ABCD. If you need to reference a rhombus, you're going to write out the word rhombus. Or you're going to write out rhomb or row, period. It doesn't matter to me as long as you get the idea that you're talking about a rhombus. All right? If a quadrilateral is made up, I'll just say of because I started making an O, of two congruent triangles, it is a parallelogram. Now you might follow that up and say, well, maybe it's not. Maybe it's a square. And I say, well, a square is a type of parallelogram, so I'm still right. Well, maybe it's not. Maybe it's a rectangle. A rectangle is a type of parallelogram. Still right. All right. So all these, a rhombus, same deal. All right. So all these different possibilities still bear out to being a parallelogram. Now you look for another possibility, like in the next one, we're